Hello, everyone. Very nice to see you all again. And although it's quite late, Happy New Year for 2021. So I believe it is time. We would like to start the 2021 winter TEIN workshop. So we will have lectures from Professor Jae-sung Lee and Dr. Min-sun Lee, and will be the moderator, and also our co-moderator will be Dr. Asmar will be our co-moderator. So I would like to welcome you all to our workshop. So before starting, if I would like to invite Professor Shamin Momtaz, if she can give us some opening remarks. Professor Shamin.
Good morning, everybody. It's our pleasure to participate today's 2021 winter workshop on physics, and I think it will give us the opportunity to learn a lot of physics related things in nuclear medicine, which we are using. And I'm very happy to seeing my lot of known faces through this workshop. And at the beginning, I would like to thank Professor Dong-Soo Lee and Professor Dr. So to arrange such type of workshop for us. And I will request all our participants to try to participate and enjoy the lectures which will be delivered through this workshop. Thank you very much.
Thank you. And could Professor Dong-Soo Lee, who is the organizer of this workshop, could you deliver us some short remarks?
Okay. Right. Just before I had a chat with Professor Shamin Lee, it was very nice to see you and see you all again, and my dear and respected Bangladesh colleagues. And this occasion, I hope this occasion might be another help for you to just get accustomed to the physics, especially deep learning based dosimetry, which would be available if you ask Professor Jae-sung Lee at the end of this presentation. So theranostic use for personalized ones are the theme. Thank you, and I just convey my microphone again to our organizer, Professor So.
Thank you very much. So we will start now. Okay, so I believe everyone can see the slides. So today, this lecture will be dedicated for the dosimetry, especially for the radiotheranostics, and also especially dedicated on the personalized dosimetry. So actually, we already have discussed about the theranostics, radiopharmaceutical theranostics at the previous summer workshop. And this theranostics is an emerging concept, which is a combined word of therapy and diagnostics. So the beauty of this theranostics is that we can actually see who will have a response using this diagnostic radiopharmaceuticals. And when we choose the patient who will get the response, we can then change it to this therapeutic radioisotope and have a therapeutic effect. So this has not been a very novel concept, but we have used this for decades by this radioiodine therapy. So as you can see from the image from the first therapy, you may imagine this patient has a effective uptake of radioiodine in the lesions, and we can assume that this patient might have a great, good response to the therapy. And as assumed at the second therapy and second scan, you can see quite improvement. So similar to this concept, by this diagnostic imaging, you can actually choose the patient who will have the response. So, so this patient, negative patient, will not go on for the therapy. And for this positive patient, we can proceed on for the lutetium targeted therapy. So at this moment, before the therapy, we can actually predict how much and how the response of this patient might be. But the other thing, after the therapy scan, what we can do is we can actually calculate how much the radiation has been delivered to this patient, which is the dosimetry. So with the emerging interest in this therapy, there has been also emerging interest for the dosimetry. So the dosimetry is a calculation and assessment of ionizing radiation dose. And actually it is like everyday procedure for radiation oncologists. They every day draw this kind of tumor target lesions, and then they draw the normal organs to actually reduce. So the purpose of this is to maximize the dose to the target and the same time reducing the dose in the adjacent organs. So we can call them like as painting a dose or the art of radiation. So this is like everyday procedure for the radiation oncologist, but for our nuclear medicine physicians, it's not that much familiar, but we do. So we have done dosimetry. So we can apply it in this treating the hyperthyroidism, such as a Graves' disease and toxic nodular goiters, by calculating the dose, how much we should deliver to the thyroid, which is calculated in. But actually, this method differs for like every countries or institutes. But like for this formula, it is based on the maximum iodine uptake. So then why should we do this dosimetry? So the purpose of the dosimetry is to deliver a lesser radiation dose to the lesion, and at the same time without causing undesired effects in other normal tissue. So actually it can be abbreviated as a AHA assay, which is as high as safely administrable. So the first part, as high, will focus on to give as high as possible to the tumor. And safely will focus on as safely means for the organ at risk to be at the safe max of below the threshold dose to this normal organs. So there is a tool strategy to give a personalized dosimetry-based administration of the radiotheranostic. The first strategy is to focus on this first part, the target tumor. So there is a known target tumor threshold dose, which is known to be, if it exceeds that dose, it will have a therapeutic effect. So we can calculate the tumor dose and we give the dose which exceeds the threshold. But however, focusing on the tumor or the lesion itself actually has some limitations in case you can imagine if the patient have too many like metastatic lesions, and if the metastatic lesions have each different uptake, it is actually hard to choose what might be our target lesion. And actually, it is impossible to accurately calculate the observed dose for each lesion. So the second strategy is to focus on this non-target organ. So this approach, this strategy is actually can be called as the maximum tolerable observed dose approach. So when you give a dose, which is the threshold dose for this organ at risk, at the same time, you can give quite at least more dose to the tumor. So if you give a maximum dose to the normal organ, at the same time, you can give more dose to the tumor. Is this what this strategy? So the non-target organ at risk actually differs based on what kind of radiopharmaceutical you are using. So for instance, what we use is iodine-131 therapy. The organ at risk that we especially care is the bone marrow toxicity. So bone marrow will be the organ at risk. But for instance, for radioembolization, liver or lung can be the organ at risk. And more recently, the lutetium dotatate or PSMA, this kidney or bone marrow can be the organ at risk. So then, how do you get the data of the threshold limit for each organ at risk? Actually, it is based on this dose effect relationship studies. And and these studies can be based on the previous radiation study results, or from like our studies regarding iodine-131 or radiation embolization. For instance, for differentiated thyroid cancer, it has been known from the previous studies that when you apply when you apply a dose which exceeds 2 gray for the bone marrow, they have seen some toxicity which is more than grade 3 or 4 and complications. So usually we use this 2 gray as a maximum threshold dose for the bone marrow. So then we know the threshold, then how can we apply this strategy to the real world? So actually, this is the study from 2018, and they have applied this maximum safe dose method for individual patients. So it might be interesting to see the enroll criteria of this study is that the patient who have no response to fixed dose, which is like when we give like 100 millicurie or 200 millicurie as a empirical dose, like this kind of fixed dose method, if the patient who had no response to this fixed dose was enrolled in this study. And they give a maximum dose which reaches 2 gray to the bone marrow. And the mean calculated the dose delivered, administered dose actually was higher than when you do the fixed dose method. And interestingly, you can see that there was response, more than 45% had a response, although all these patients were a patient which had no response to the iodine therapy. So, and at the same time, there had some transient cytopenia, however, which had recovered after a month. So when you give this maximal safe dose, you can have achieved such a response, but at the same time, a minimal toxicity. So there has been another study which head-to-head comparison of the maximum dose method compared to the empirical fixed dose. And as you can imagine, compared to this fixed dose method, dosimetry based this individual administration showed a improvement in the survival. And this also gave the dose of maximum of 2 gray to the bone marrow. And as you can also see, the dose delivered to the patient was higher in this maximum safe dose approach. But at the same time, there was no significant difference in compared to this fixed method of the toxicity. So not only for this iodine therapy, but also there has been this personalized approach for the radiation embolization therapy. So this study is actually, the purpose of this study is to see the prognostic score. However, we may focus on how they have delivered, choose the dose, and their strategy was based on this maximum safe dose, and the target at risk, what they have chosen was the liver. And they give the dose which reaches the maximum dose to liver initially as a 40 gray. And at this level, because there was no toxicity, they move on to the 70 gray. And when delivered this maximum tolerated dose, the patient had a median overall survival of 14.1 months. Compared to the previous studies of this radioembolization using the standard dose, they shown that there is some improvement. However, this is not a head-to-head comparison study, so we could not actually conclude. However, the next study actually compared whether this personalized dosimetry will have a more efficacy compared to the standard method. Actually, this group focused on not only the second strategy, which is the maximum tolerable dose. However, they actually have focused on the first strategy to give a more than threshold dose to the tumor, which is 205 gray, more than 205 gray to the tumor. And at the same time, less than 120 gray to the liver and less than 30 gray to the lung was how they personalized the dose. Compared to that, when you see the standard method actually give a dose of 120 gray to the perfused lobe. So when you see this table, you can see that absorbed dose to the tumor is actually higher in this personalized dosimetry group. And as a result, there has been a gain, improvement in this overall survival compared to the standard dosimetry method. So now we have seen that this personalized dosimetry has some efficacy and at the same time, minimal toxicity in the iodine therapy and radiation embolization. And more recently, it has been applied to this novel diagnostic with PRRT. And from this NETTER-1 clinical trial, this lutetium dotatate have been approved as got an FDA approval, and now it's widely used in the clinic. However, if you see the label, FDA label of this Lutathera, you can find out that the dosage and administration dosage is actually, it is given at a fixed dose of 200 millicurie at 4 cycles. So we do not do a personalized based method for this Lutathera. However, there has been a group to see whether there is a improvement efficacy if we give not this fixed dose, but like a personalized dose. So this prospective study actually have done a study and chosen a maximum safe dose, which reaches a kidney dose to 23 gray. And as you can see, the patient who reaches this maximum safe dose will have more dose delivered to the tumor. So as a as a result, the patient who reaches the 23 grade to the kidney has shown a better progression-free survival or overall survival. From this kind of study, there has been an ongoing clinical trial, which is really going to see the efficacy of applying this personalized dosimetry. And most of the studies are quite similar, but in detail, they are different. But you can see the first study was also, which is called Illuminate, also chose the organ at risk as a kidney. So they choose the kidney and maximum tolerable dose as 27 grade to the kidney. So their strategy is to give every time 200 millicurie for not a limited cycle, but when the accumulated kidney dose reaches 27 grade, they stop. So like patient can have 4 times therapy, or some patient which have a low dose to the kidney, who can have more, like 6 or 8 times of therapy. And after that, patient who had no toxicity move on to the second step, which the tolerable limit dose was upper to the 40 grade. So as you can see, when the Lutathera right now is actually limited for the 4 cycle of 200 millicurie for 4 cycle dose. However, when you apply this personalized dosimetry as a maximum tolerable dose approach, you can see quite a lot of patients had got like more than 4 cycle of 5, 6, or 7, or 8 cycles of therapy, which will actually, as a result, come out with better response. However, now this result is just an interim result. We are actually waiting for the more follow-up result. And you can see the kidney toxicity, there was a decline in the renal function. However, no grade 3 or 4 toxicity was observed in this approach. And next study is also similar, and they also chose a kidney as a maximum, the organ at risk. And the target dose was 23 grade as a total. So you can see that although patients, so what's their strategy was to give to reach 6th grade to the kidney for every cycle. So you can see, although the kidney dose for each cycle is 6th grade, the administered dose is every time different. Like for the second therapy, 14.6 was delivered, and for this 14.6 gigabecquerel, the calculated dose will be 6th grade, and for 21.9 gigabecquerel, the calculated kidney dose will be 6th grade. So the total will be, for the first will be 5 grade, so the total will be 23 grade. Then when applying this kind of maximum tolerable dose, they have seen that like the response was more than 50% of patients had a response to this therapy. And as you can imagine, the absorbed dose to the tumor actually is higher when you apply a personalized dosimetry. But at the same time, no significant difference, no significant toxicity was observed, but some toxicity regarding the bone marrow related toxicity was observed actually, and most was related to the lymphocytopenia, which actually improved, which turned out to be a transient lymphocytopenia. So we now have seen that when applying a personalized dosimetry, especially when we use a strategy of maximum safe dose approach, we can actually deliver a more dose compared to the standard empirical method. and at the same time, without no significant increase in the normal organ toxicity. So then, how can we really do this organ-based dosimetry? So this dosimetry. So first method is organ-based dosimetry. And this is actually a standard method in nuclear medicine field right now. And actually it is simple and it can do a fast calculation. So the important point in the organ-based dosimetry is the source organ and the target organ. So you can actually get the dose for each organ, and every organ can be a target organ. But when you assume, let's assume that we want to calculate the absorbed dose in the liver, and liver as a target organ, then what organ can have an effect, radiation effect on this liver? So firstly, the liver itself can have a radiation to the liver, and more adjacent organs such as kidney or spleen can have a radiation effect. And also salivary gland or bladder can have a radiation effect to the liver. So these organs with some significant uptake can be regarded as a source organ. So for assuming for PSMA, the source organs can be salivary gland, liver, spleen, kidney, or bladder. And when after choosing the source organ, you have to now calculate the cumulative activity for each source organ. So how to do that is by this 3 steps. So the first, you have to acquire a multi-time point data. And after that, you need to get a activity for each time point, for each organs, each source organs. Then you can get a time activity, this kind of time activity curve for each source organs. Then when you calculate the area under the curve to the time, infinite time, you can get a cumulative activity for each source organs. Now, so you have a sum of cumulative activity of each source organ, then now you can actually calculate the observed dose to the target organ. However, to translate this cumulative activity to the absorbed dose, we need a S factor, which is a energy transfer from the source organ to target organ. And actually this S factor depends on the radiation type, energy, and anatomical relationship. So you can imagine, and this is actually provided by based on Monte Carlo simulation from phantoms. So this is a MURD pamphlet, and according to and it's a pamphlet from the iodine 131. So let's imagine thyroid as a source organ. So there is an uptake in the thyroid. And this source organ, what do you think might have the most radiation effect, radiation from this thyroid? So you can think easily that thyroid itself will have the highest radiation from the thyroid itself. So the S factor of the thyroid actually is the highest. And as the anatomical position gets more distant organ, like for lung, it's lower than the thyroid. However, the kidney is more lower than the lung because of its anatomical relationship. So this S factor is actually depends on not only the radiation type and energy, but also the anatomical relationship and also the densities. So now you have the S value. So you can actually calculate from the cumulative activity and S value the absorbed dose. And after that, but however, there is a problem of this organ-based dosimetry using this S factor, because this S factor is actually based on from this MURD phantom, which is not a individual man. So actually it cannot reflect more specific patient or individual patients. And also it actually, there is an assumption that the organ distribution of radiopharmaceutical is uniform. And this medium has a uniform distribution, which is not actually true in a real situation. So this organ-based dosimetry is not patient-specific. So there has been some method to actually to solve this kind of problem, which is the Voxel-based dosimetry method. And it is based on a Voxel-based Monte Carlo simulation, and each voxels are regarded as a single organ. And actually, this method is independent to the standard human anatomy, and the heterogeneous activity distribution are acceptable using this method. However, the problem is when you do Monte Carlo simulation for every voxel, it takes too much expensive computational cost and time. So recently, Professor Jae-sung Lee and Dr. Min-sung Lee have proposed a more simplified method of using multiple voxel S-value approach, which will be more discussed by Professor Jae-sung Lee and Dr. Min-sung Lee from the following lectures. So with this method and knowledge, we need to actually gather more evidence. Actually, I have shown that there are ongoing clinical trials, but they are not like randomized controlled clinical trials. So actually the evidence levels of these ongoing clinical trials is not also that high. So there is a need to collect more data to show whether this personalized dosimetry is real, applicable to actually apply in real clinical situation. So thank you for listening to the introduction, and following lectures will be delivered by Professor Jae-sung Lee and Dr. Min-sung Lee. And I would like to invite Dr. Asmar for the moderation.
Thank you, Professor Min-suk Soo. উপস্থিত সুধী আসসালামু আলাইকুম। এরপরে আমাদের মূল বক্তৃতামালা শুরু হচ্ছে। এরপরে 4টি বক্তৃতা রয়েছে। প্রথমে বক্তৃতা দেবেন অধ্যাপক ডক্টর জে-সং লি। তিনি স্নাতকোত্তর ডিগ্রি নিয়েছেন 1996 সালে ইলেকট্রিক্যাল ইঞ্জিনিয়ারিং বিষয়ে এবং পরবর্তীতে 2001-এ পিএইচডি সম্পন্ন করেছেন বায়োমেডিক্যাল ইঞ্জিনিয়ারিং বিষয়ে। দুটো ডিগ্রি তিনি নিয়েছিলেন সোল ন্যাশনাল ইউনিভার্সিটি থেকে। এখানে উল্লেখ্য, সোল ন্যাশনাল ইউনিভার্সিটি এশীয় বিশ্ববিদ্যালয়গুলোর মধ্যে 9ম এবং বৈশ্বিক র্যাঙ্কিংয়ে বর্তমানে 60তম অবস্থানে রয়েছে। 2005-এ তিনি সোল ন্যাশনাল ইউনিভার্সিটির কলেজ অফ মেডিসিনে যোগদান করেন। বর্তমানে তিনি একাধারে প্রফেসর অফ নিউক্লিয়ার মেডিসিন, বায়োমেডিক্যাল ইঞ্জিনিয়ারিং এবং বায়োমেডিক্যাল সায়েন্স হিসেবে দায়িত্ব পালন করে চলেছেন। প্রফেসর জে-সং লির একাডেমিক অ্যাচিভমেন্টের মধ্যে বিশেষ উল্লেখ্য হলো ইমেজ অ্যানালাইসিস এবং পেট সিস্টেম ডেভেলপমেন্ট সংক্রান্ত কিছু গুরুত্বপূর্ণ উদ্ভাবন, যা তাকে এবং সোল ন্যাশনাল ইউনিভার্সিটিকে এনে দিয়েছে জগৎজোড়া খ্যাতি। বর্তমানে তার অধীনে মেডিকেল ইমেজিং মোডালিটির উন্নয়ন ও পার্সোনালাইজড ডোজিমেট্রি সংক্রান্ত গবেষণা কর্মকাণ্ড পরিচালিত হচ্ছে। আজকের কর্মশালায় প্রফেসর জে-সং লি 2টি বক্তৃতা দেবেন। প্রথমটির বিষয়বস্তু ইন্টারনাল ডোজিমেট্রির বেসিক ফিজিক্স এবং পরেরটি ডোজিমেট্রিতে ওনার উদ্ভাবন ভক্সেল বেসড এবং মেশিন বেসড কিছু মেথড, যা নিকট ভবিষ্যৎ দিনের নিউক্লিয়ার মেডিসিনকে এক অনন্য বৈশিষ্ট্যে মণ্ডিত করবে। তবে আর দেরি নয় সম্মানিত সুধী, প্লিজ ওয়েলকাম প্রফেসর জে-সং লি।
Thank you for your kind introduction. 서민 선생님, 그 화면 공유 좀, 네네. So let me share my screen.
Just before starting Professor Jae-Sung-Lee's lecture, I would like to inform everyone that if you have any questions or comments in between the lecture, please, you can write down freely on the chat, and then we can discuss after the lecture. Thank you very much.
Okay. Yeah, so if you have any question, yeah, please leave the questions in the chatting window. Okay. As I introduced, my name is Jae-Sung Lee in Seoul National University. Today, so I wanna, deliver two different lectures. So one of them is the basic physics for internal dosimetry, and second, the lecture that will given after Dr. Minson-Lee's talk will be about the voxel-based dosimetry, patient-specific voxel-based dosimetry. Okay. So let me start with the basic physics that might be useful for understanding the internal dosimetry. Okay. So actually, as you know, there are two forms of radiation. So the one of them is the particulate radiation that is accelerated in atomic or subatomic particles, such as electrons and protons. And because that they are particles, they have kinetic energy or mass when they move. And the second type of radiation is electromagnetic waves. So this electromagnetic radiation oscillate electrical and magnetic. The is the oscillating electrical and magnetic field that travel through space at the speed of light. So that is why that they are the wave-like, or sometimes that the packet-like energy. So that is why that they are called the photon or quanta, and they doesn't have mass or electrical charge. So this slide shows the relationship between the energy and the frequency and wavelengths of electromagnetic wave. So yeah, as you may know, that the with higher the frequency, the electromagnetic wave has higher energy, and the frequency and the wavelengths have the actually that their multiplication is constant. I mean that if we multiply the frequency and wavelengths, it equals to the speed of light, as you can see here. Okay. So actually, this this figure shows the such energy spectrum and the spectrum of the frequency spectrum of electromagnetic waves. So as you know that the gamma ray and X-ray lay in the right side of this spectrum. It means that they have high frequency and they have higher energy than the ultraviolet or visual light or something like that. Yeah, so this electromagnetic wave, as I told you, that they are also regarded as a photon. And this slide summarizes how these photons interact with the atom. Actually, that these photons, electromagnetic wave interact with the atom with some different kind of mechanism. One of them is Rayleigh scattering. The second is Compton scattering, photoelectric absorption, and another the interaction and pair production. What is Rayleigh scattering? Yeah, actually, that in the Rayleigh scattering, the incident photon and scattered photon has same wavelengths. It means that the energy has not been changed in this mechanism. I mean that this photon has changed its direction without lose any energy. Okay. Actually, that this Rayleigh scattering occurs mainly with very low energy photons. So they may not be in a range of the photons that we used in the nuclear medicine. But the Compton scattering is one of predominant interaction of photons in the diagnostic energy range with soft tissue. I mean that the one of the main mechanism of photon interaction in the nuclear medicine, the photons in nuclear medicine. Yeah, actually, differently from the Rayleigh scattering in the Rayleigh scattering, the photons the wavelength of the photons is changing if it the change its direction like that. I mean that the scattered photon has longer wavelength than the incident photon, as you can see here. It means that this scattered photon has lower energy than the original incident photon. Okay. Yeah, and actually, the lost energy in this interaction is used to eject Compton electron, as you can see here. So this Compton electron, is generated by the energy of this instance photon. Okay. Then what is photoelectric absorption? Yeah, actually in the photoelectric absorption, the instance photon totally disappear, as you can see here. And that all of this energy has been used to eject this electron. Okay, so the energy of instance photon should be higher than the binding energy of this electron, and the kinetic energy of this photoelectron have is the difference between the energy of instance photon and the binding energy of this electron. Okay. So if electron is ejected from this area, what will happen? Yeah, actually that it will cause it will lead to some creation of a vacancy here, and if some vacancy is created here, actually that the electrons in the upper shell is likely to move to the lower shell to fill this vacancy. So that is why that the characteristic X-ray is generated, and each energy is the difference between the binding energy of these shells. Okay. The last of the photon interaction is the pair production. Actually, the pair production only occurs by high energy instance photons. I mean that the energy of instance photon should be higher than 1.02 mega electron volt. Okay. Yeah, actually in this case, that the instance photon disappear by the interaction with this the nucleus of atom, and two particles are generated. I mean that when this photon disappear, two particles are generated, and they are electron and positron. I mean that the positron and electron pair are pair is generated by this instance photon. Okay. So it means that the photon's energy is transformed to the two particles. Okay, and what will happen if this positron is generated? Actually, this is quite the same as the principle of path, because that the positron is likely to meet electron, and that once they meet each other, their mass disappeared, and this mass is converted into two 511 kilo electron volt gamma ray photons. So annihilation photons are generated. Okay, so usually this annihilation photon generation to follow this the pair production. Okay. So yeah, so this slide show the which interaction mechanism is dominant. depending on the energy of photon. Okay, I mean, that in the low energy photon, with the low energy photon, the photoelectric absorption is dominant. Okay, but if energy get higher, so if energy is higher than 5 kilo electron volt or something like that, actually the Compton effect is more dominant. Okay, but with very high energy, I mean that the mega electron volt range, the pair production is dominant. Okay, so I think this is quite important the mechanism of photon induction. Okay, yeah, so actually I have summarized what is the possible interaction of photon with the atoms. But the particle interaction is quite different from the photon interaction. I mean that the particles of ionizing radiation interact with the atoms with with different mechanism. Okay. Anyway, that there are the charged particles. Actually, these charged particles include alpha particle, the proton, positron, and electron and beta particles, and the neutron is uncharged particle. Okay. So as I told you, the behavior of these particles with the charge and mass passing through the material is very, very different from the behavior of photons. Okay, how different? So before talking about the mechanism, the interaction mechanism, so let me summarize what is alpha and beta rays. Okay, so yeah, as you know, that the alpha decay is the decay mode that occur primarily among very heavy electrons. Okay, and this very heavy electron emit alpha particle that equals to the atom of helium. Okay, 2 protons and 2 neutrons. This alpha particle has the kinetic energy of approximately 4 to 8 mega electron volt, and the range of this alpha particle is only about 30 micron. Okay, 30 micron in body tissue. After this alpha decay, atom mass is decreased by 4 because alpha particle is a combination of 2 protons and 2 neutrons, as I told you. Another important factor that we should keep in mind, usually that after this alpha particle, the cascading, the decay of atom usually happen. For example, that the uranium-238, actually that after emitting the alpha particle, each donor emit beta minus, and each granddaughter also emit beta minus, and alpha and some cascade alpha and beta rays. So lots of that the radiations, particle radiations are generated once uranium-238 started to the decay. Okay, so lots of energy are transferred to the tissue. So let me move to the beta minus emission. Actually, that as you know, the beta minus emission happen in the radionuclide with excess number of neutrons compared to the number of protons. So actually, that the one of neutron is converted into proton with the simultaneous ejection of negatively charged beta and anti-neutron. Okay. So this slide shows such a decay scheme of beta minus emission. I mean, because that in the beta minus emission, atomic number increase, it goes to right there. Okay. Actually, the carbon-14 only emit beta minus. Yeah, I mean that it is a kind of, the pure beta minus emitters. Okay, it only emit, beta minus. Okay, so these, these, pure beta minus emitters include, hydrogen 3, carbon 14, and phosphate 32. Okay. Yeah, as I told you, that when beta minus is emitted, actually, that the antineutrino is simultaneously ejected with this, beta minus particle. So it means that, that the beta minus and antineutrino will, compete with each other to get, more energy. So that is why, that the beta minus share the energy with, antineutrino. The energy of beta is quite uncertain. I mean that the, beta minus will have, such a continuous, energy spectrum. Okay, energy spectrum. So we only know what will be the, maximum energy of beta minus. Okay, so the beta minus particle emitted from the, carbon 14 has, a maximum energy of 156 kiloelectron volt. Okay. We can also define, that the average energy. I mean that the average energy of beta minus is approximately, 1/3 of, maximum. So yeah, so that is why, that the average energy is about, 500 kiloelectron volt. Okay. Please also remember that, the beta particle can penetrate, only relatively small thickness of, solid materials. Okay, few millimeters. You should also remember what is, beta minus and gamma emission. Okay. Actually, that any, the excess energy in the nucleus following beta decays emitted as, gamma rays or internal conversion of electrons or other associated radiation. What does it mean? It means that, that there are some unstable nucleus emitted, beta minus. But even after the emission of beta minus, this atom is still unstable. So because of that, instability, even after the beta minus, it should emit, some additional energy in the form of, gamma ray. So look at this, this guy, this X emitted beta minus. So it is converted into the Y star, but this Y star is still unstable. It has not been, satisfied, unstable. So the additional energy should be released in the form of, gamma ray. So that is why, that the beta minus and gamma, emitted, from the excitation, this decay. Okay. So is this good or bad? What do you like? Do you like a pure beta minus emission or beta minus gamma? Yeah, I may prefer this beta minus gamma because, that we can utilize this beta minus for therapy and this gamma for imaging. I mean that we can do the theranostics using this beta minus gamma, the emitting radioisotopes, right? So that is why, that this beta minus gamma emitter are widely used for, the nuclear medicine therapy. So for example, iodine-131 is one of such that emit, beta minus and gamma. Okay. And another, popular one is, lutetium-177. It also emit, beta minus gamma. Okay. So look at this. So this is another beta minus gamma emitter. The Xenon-133. It emits, beta minus and gamma. Okay. Yes. So I think you can now, the reminded what is alpha and beta and gamma. Okay. Then let me move to the interaction of charged particle. Yeah, actually, as I told you, the charged particle, the behavior of charged particle is different from the photons. The charged particle usually leads to the excitation or the ionization of the atom. Okay. Yeah, as you know that the excitation is the elevation of electrons to excited state in atom, molecules, or a crystal. And ionization is the removal of electrons from atoms or molecules. Okay. So this slide shows the detail of excitation. Okay. Actually, that this charged particle, the positive charged particle, is moving around in atom, and due to the each Coulomb force, the charge, the initial electron has moved to the upper shell like that. So the overall energy of this atom is increased. So it means that it is excited. Okay. Yeah. So what will happen if this electron is raised to the higher shell? Yeah. Actually, that because of this vacancy, the upper shell of electrons will move to the inner shell. Okay. Then each energy will be released in the form of electromagnetic wave. Okay. I mean that the X-ray. Yeah, so that is why that the characteristic X-ray is generated following this excitation. Okay. So you can see what is the characteristic X-ray that has some unique value. Okay, that is the difference of between the binding energy of this inner shell and the outer shell. Okay. But OJ electron can also happen. I mean, as I told you, that if there is a vacancy is generated due to the excitation, the electrons in the upper shell is likely to move to the inner shell. Then the characteristic X-ray will be generated, and the energy of the characteristic X-ray is the same as the difference between the binding energy of these two shells. Yeah, but instead of the generation of characteristic X-ray, this energy difference can be used to eject some outer shell electrons. Okay, so this is the OJ electron. I mean that instead of generating characteristic X-ray, the OJ electron is empty. The energy is used to release this electron. And the kinetic energy of OJ electron will be same as the energy of the binding energy of the inner shell minus 2 times of binding energy of the outer shell. Okay. The second interaction mechanism is ionization. Yeah, actually, that the ionization occurs when transfer the energy exceeds the binding energy of the electron as well. Okay, I mean that the instance actually the charged particle is moving like that, and if the charged particle energy is higher than the binding energy of this electron, actually this electron will be ejected like that. Okay. So it will cause the ionization of this ion, this atom. Okay, I mean that the ion pair is generated. The pair of electron and positive ion is generated. Okay, and if we know that this electron has the sufficiently high energy, it can behavior like secondary electron. I mean, it can cause another ion. It can lead to another ionization. Okay, so usually we call this secondary electron delta A. Okay, so some cascading ionization can be occurred. Okay. Let me now tell you some important the nomenclatures used in dosimetry. The one of them is specific ionization. So what is a specific ionization? Yeah, actually the definition of specific ionization is the number of primary and secondary ion pairs. So you have learned what is primary and secondary ionization. Okay. By the way, number of primary and secondary ion pairs produced per unit length of charged particle path. It means how many ion pairs has been generated per unit length due to the this charged particle interaction. Okay. So yeah, if the particle has the electrical charge, I mean that if the particle's electrical charge is high, it will cause the more number of additional specific ionization. So I mean that the specific ionization increases with the electric charge of the particle. Okay. So what is the relationship between the particle velocity and specific ionization? If that actually that the specific ionization decrease with instance particle velocity. I mean, if the particle moves so quickly, so fast, the probability of interaction between the particle and the atom will decrease because it is too fast. There is no chance for interaction. So the slow particle is more likely to interact with atoms. So that is why the specific ionization decrease with instance at the particle velocity. The typical value of specific ionization of alpha particle is as high as 7,000 ion pair per milliliter in air. And the typical value of specific ionization of electron between 50 ranges between 50 to 100 ion pair per centimeter in air. Okay, so you can figure out alpha particle has a higher specific ionization than electron. Okay, I think you have heard about Bragg peak. Yeah, Bragg peak is a very important concept, especially in the charged particle therapy. Yeah, actually, the x-axis is distance from the end of range, and y-axis is specific ionization. I mean that the ion pairs per milliliter. Okay. Yeah, actually, the imagine the charged particle is coming from air to some material. Actually, initially, each velocity is very fast. Yeah, it is very fast, quickly moving. So the interaction probability is low. So small number of ion pairs are generated. Only small number of ion pairs are generated. But as the charged particle is moving, it loses its energy. So it gets slower. So as it as the each velocity is decreased, the probability of interaction will increase. That is why more number of ion pairs are generated. Okay. So in some point, this specific ionization reaches to the peak, and after this peak, it loses all of the energy, then it will stop. Like that. So that is why that the number of ionization doesn't have peak at the entrance, and it has peak at some distance like that. Okay, so this we say this is bright peak. Charged particle tracks. Actually, the alpha particle and beta particle has a different the particle tree. So as you know that the alpha particle is a very strong guy, so that is why it moves straight. Okay, so that is why the alpha particle's path equal to each range. But the beta minus, actually, it is very light guy, so it is easily affected by the surrounding atoms. So that is why that this guy is moving around like that. Okay. So the path and length range different. I mean that each path is much longer than each range. Okay. So let me now tell you what is linear energy transfer. Linear energy transfer is LET. Okay. So this is very, very important the quantity used in dosimetry. Okay. Please remember this linear energy transfer. Okay. Actually, definition of linear energy transfer is the amount of energy deposited per unit path length. Okay. Look at this, electron volt per centimeter. Energy deposited per unit path length. Okay. This linear energy transfer is the product of specific ionization and average energy deposited per ion pair. Okay. So electron volt per ion pair. So this is an ion pair per centimeter. So if you multiply these two terms, it will be electron volt per centimeter. Okay. Energy, amount of energy deposited per unit path length. So this is why that this LET largely determines biology consequence of radiation exposure. Okay. Alpha and proton has high LET, and the electron and gamma ray has low LET. Okay. So this is why that the alpha has the more severe biological consequence than electron or the gamma. Okay. I think, yeah, actually this is very famous, the picture that shows the LET and the way of infection of alpha and beta. Yeah, as I told you, that the alpha has high specific ionization, and the alpha has high energy usually. So that is why the LET, that is the the product of specific ionization and each energy ranges 50 to 230 kiloelectron volt per micrometer. This is quite high. Okay, I mean that it loses lot of very high energy in very short distance. Okay, short range. And as I told you, that the alpha particle goes straight like that. So it is very likely that it will cause the break of this binding on both sides. Okay. But how about battery? Yeah, as I told you, that the battery has lower specific ionization than alpha, and usually energy is also lower than alpha. So that is why the specific, that the linear energy transfer is low, as you can see here. It is about 0.2 kilo electron volt, and beta is moving around like that. So we are not sure whether it will break both the this point. Okay. But how about OJ electron? Yeah, OJ electron has lower initial kinetic energy than battery, because the energy, the initial kinetic energy of OJ electron is the difference between the binding energies. So it is quite small. So that is why OJ electron is quite slow. So either has high specific ionization, okay, and its linear energy transfer is higher than beta, okay. So the therapeutic effect of OJ electron would be higher than beta minus. Yeah. So actually, that in my the first lecture, the physics for the dosimetry. So I told you there are two different types of radiation. The first one is electromagnetic wave, and the second one is particulate radiation. And their interaction mechanism is different. I mean that the photons interact with the atom under 4 different mechanisms: Rayleigh scattering, Compton scattering, photon interaction, and pair production. Okay, and their dominance is different depending on the energy of instance photon. Okay, how about the particles? Yeah, charged particles can cause ionization or excitation. Okay, so excitation will be followed by characteristic X-ray or the OJ electron. Okay, and that I would like to ask you to remember two terminologies: specific ionization and linear energy transfer. The specific ionization is the number of ionization generated per the unit length, okay, and this specific ionization increases with the charge of a particle and decreased with the the velocity of particles. Okay, and what is the linear energy transfer? Linear energy transfer is the product of specific ionization and the energy of particle, and the specific ionization and average energy deposit per ion pair. Okay, and this linear energy transfer determines biological consequence, and alpha has the highest linear energy transfer, and beta linear energy transfer is lower than alpha, and OJ electron is in between. Okay, that's it. So if you have any question, yeah, please ask me, or you can leave your questions on chatting window. Do you have any questions?
May I introduce you to our colleagues in Bangladesh in my language, and before you start your lecture?
Okay, sure. Thank you. Yes, please go ahead. Can you hear me?
উপস্থিত সুধী, এখন বক্তৃতা দেবেন ডক্টর মিনসান লি। তিনি স্নাতকোত্তর ডিগ্রি প্রাপ্ত হয়েছেন 2012 সালে নিউক্লিয়ার ইঞ্জিনিয়ারিং বিষয়ে, এবং পরবর্তীতে 2018-তে পিএইচডি সম্পন্ন করেছেন রেডিয়েশন অ্যাপ্লাইড সায়েন্স বিষয়ে। 2টো ডিগ্রি তিনি নিয়েছেন সোল ন্যাশনাল ইউনিভার্সিটি থেকে। 2020-এ তিনি কোরিয়া অ্যাটমিক এনার্জি রিসার্চ ইনস্টিটিউটে যোগদান করেন এবং বর্তমানে তিনি সেখানে নিউক্লিয়ার এমার্জেন্সি অ্যান্ড এনভায়রনমেন্টাল প্রোটেকশন ডিভিশনে সিনিয়র রিসার্চার হিসেবে কর্মরত আছেন। ডক্টর মিন সান লির গবেষণার বিষয়বস্তু মেডিকেল ফিজিক্স ইন ইমেজ অ্যাকুইজিশন এবং ভক্সেল-বেসড ডোজিমেট্রি। তিনি অবশ্য আজকের কর্মশালায় অর্গান-বেসড ডোজিমেট্রি সম্পর্কে আমাদেরকে ধারণা দেবেন। উপস্থিত শ্রুতি, প্লিজ ওয়েলকাম ডক্টর মিন সান লি।
Thank you very much for your introduction. Hello, my name is Min-sun Lee from Korea Atomic Energy Research Institute, and today I will be giving a lecture about organ-based dosimetry. If you have any question during the lecture, please feel free to ask any question. So this is the context of this lecture. I will be briefly talking about the basic background about the radiation dosimetry, and then we will go through the calculation of radiation dosimetry doses step by step. And then finally, I will be showing an example of organ-based dosimetry. So in the first basic background section, I will be talking about the terms and concept of the radiation dosimetry. So I would like to introduce few terms and concepts that is widely used in the radiation dosimetry. First of all, what is radiation dosimetry? As a general terminology, radiation dosimetry means the measurement of the deposited energy in the human body that is delivered by the ionizing radiation. Biologically, it means that measurement of the radiation-induced changes in the body organism. And physically, it means measurement of the deposited energy, which is joule per unit mass of kilogram. This radiation terminology is widely used in both medical field, such as nuclear medicine, and also radiation oncology, and also radiation environmental analysis as well. In this lecture, we are going to focus on the radiation dosimetry, especially in the nuclear medicine field, which is called the internal radiation dosimetry. So this internal radiation dosimetry specifically is defined as measurement of the radiation energy that is deposited in the internal organs of the human body, and that is delivered by the radiopharmaceutical uptake. And from now on, I will be focusing on the radiation dosimetry specified in the nuclear medicine field. So measuring the internal radiation dose delivered from the radiopharmaceutical uptake is especially challenging compared to the radiation dosimetry that is widely used in the external radiation beam therapies. So it's rather very complicated to measure the radiation doses inside a body because it cannot be measured directly. However, this radiation dosimetry in the internal organs are very important and necessary to analyze the energy distribution in the body tissue quantitatively to ensure the accurate therapeutic prescription. Also, it is very important to assess some potential risk for the patients as well. Should I stop here a little bit for your translation or continue?
그냥 진행하시면 될 것 같아요.
진행하면 돼요? 네.
특별히 번역은 안 하고 있습니다.
네. So the basic terminology that is widely used in the radiation dosimetry is the absorbed dose, which is described as alphabetical letter D. This absorbed dose is defined as the amount of radiation energy joule that is deposited in the unit mass of organ in unit of kilogram. So this absorbed dose has the unit of joule per kilogram, which is energy per unit mass. And in a basic SI unit, we widely use the unit of Gray, which is defined as GY, as you can see here. And this 1 Gray of absorbed dose is defined as 1 joule energy deposited per kilogram absorber. So this is the, I guess you already have seen this unit before. This Gray unit is the most widely used unit for the absorbed dose. And also there is also other traditional unit that was used previously, which is a unit of rad. And this 1 rad of absorbed dose is defined as 100 erg energy deposited per gram absorber. And this is same as 0.01 Gray of absorbed dose. So absorbed dose is defined as the energy per unit mass of organ. However, this absorbed dose terminology is not specified in the organ. It can be also widely applied to the other materials as well. So yeah, I would like to note that this terminology can be applied to any kind of absorber materials. So the second terminology that I would like to introduce is the equivalent dose and the effective dose, that is shown as letter H and E. This two terminology is very similar to the absorbed dose D that I have introduced you in the previous slide. However, this two equivalent dose and effective dose quantity takes account into the relative biological damage that is caused by the radiation interacting with the tissue. So this definition of equivalent and effective dose takes into account of biological information and also the characteristic that is related to the radiation. This equivalent dose can be defined as the tissue damage per Gray of absorbed dose. And as I mentioned, since it takes into account of biological damage, this terminology depends on the type of radiation and also the energy of radiation. And also it depends on how exactly the radiation deposits its energy to the tissue. So this equivalent dose and effective dose has a unit of called sievert, which is written as SV, like this. I guess you've seen this unit for several times, I guess. And this equivalent dose, H, in unit of sievert can be simply calculated by multiplying the absorbed dose in the unit of Gray by multiplying with the weighting factor, WR. This weighting factor is, you can check up on this table on the right top, which is, this is the weighting factor for the different types of radiation for the calculation of equivalent dose. So depending on the radiation that you use for the medical purpose, they have the different weighting factor, because depending on the radiation type, they have different energies and different penetration powers. For example, for the radiation that is widely used for imaging, X-rays, gamma rays, they have the weighting factor of 1, which means that the effective equivalent dose will be same as the absorbed dose. However, for the particles such as neutrons, protons, and alpha particles, which have a very low penetrating power, they have a higher weighting factor of, for example, alpha particle have 20 of the weighting particle WR, which means that you will have more biological damage caused by the radiation. And then this effective dose E in the unit of sievert, they do have a same unit. This one can be calculated by multiplying this equivalent dose H with the weighting factor WT. And this weighting factor, you can check this value in this table on the right bottom. And This is the weighting factor of tissue for the calculation of effective dose. Depending on the internal organs, they have a different weighting factor. So for example, for the rat marrow, colon, lungs, and stomach, the weighting factor is 0.12. However, compared to this, such as organs that is very thick or very thin, such as brain, skin, salivary glands, bones, surfaces, they have the very low weighting factor of WT. So depending on the organ or tissues in your interest, we need to introduce different weighting factor of WT to calculate the proper effective dose. So I have introduced the definition of radiation dosimetry, also terminology of observed dose, effective dose, and equivalent dose previously that is widely used in the radiation dosimetry studies. And from now on, I will be talking about the calculation of radiation dose. And in this lecture, I'm going to specially focus on the MERD method. So how can you calculate the radiation dose of the internal body or organs? As I mentioned in the first slide, the radiation dose inside the human body cannot be measured directly because we cannot put any kind of dosimeters inside the organs, and also the radiation pharmaceutical circulates all over the body, and we do not know where this will go, so it is very challenging to measure directly. So generally, we use an image-based analysis using the PET or SPECT images for the dosimetry in the nuclear medicine field. Since the PET has the quantitative, provides a quantitative images, because each of PET voxels contains the radioactivity information, which has a unit of becquerel per milliliter. So we can quantify each voxels of PET. So we can perform some quantitative analysis using the PET images. So for an example, the widely used quantitative image analysis technique in PET is the SUV, which is the standard optic value, by drawing a region of interest on the PET images. And when we extract the voxel information from this ROI, we can calculate this SUV value as this equation. This SUV value is a semi-quantitative value to analyze the radiation source distribution inside the body or patient. However, this does not represent the radiation doses at specific organs. So to extract the dose information from the PET images, how can you do? So first of all, we need to have the pharmacokinetic distribution of the radio tracers. Because since depending on the radiopharmaceutical distribution throughout the time, you will have the different dose values inside the organs. And to obtain this pharmacokinetic distribution, we need to have the dynamic PET scan as a first step. And then based on the dynamic PET scan, we will need a proper dosimetric model to calculate the dose values inside the organs. So I mentioned about two things to have the accurate dose calculation inside the body. Firstly, we need a pharmacokinetic distribution, and second, we need a proper dosimetric model. There is one committee that is called Medical Internal Radiation Dose, abbreviated in MERD, and this committee is established within the Society of Nuclear Medicine Society, SNM, in 1965. And this committee is establish it to develop standard methods, models, and also mathematical schemas, and they do publish data for assessing the internal radiation doses. There are a series of reports that is called MERT pamphlets, which contains very useful information about the dosimetric methodologies and also mathematical schemas, and also some data as well. And MERT pamphlet number 21, this one is the latest publication of MERT-based dose calculation. So if you're interested, you can check up on this MERT pamphlet number 21 for more detailed information about the radiation dosimetry that is suggested by this MERT committee. So today's lecture topic is the organ-based dosimetry. And the organ-based dosimetry approach is basically suggested by the MERT committee that I introduced in the previous slide. And therefore, this organ-based dosimetry is also called as MERT schema. This organ-based dosimetry calculates the radiation dose that is delivered in the organ level. So depending on your target organ, they calculate the radiation absorbed dose. And this organ-based dosimetry approach is used as a gold standard of the internal radiation dosimetry. So the MERT committee had suggested this organ-based dosimetry a long time ago, and they defined the absorbed dose with the following equation. We have already dealt with this terminology of absorbed dose, which was the deposited energy from the radiation to the target organ or target unit mass of organ. So this absorbed dose of the target region, RT, from the activity from a source or region, which is RS, can be calculated as the cumulated activity, which is defined, which is shown as A tilde in this equation, times the S value, which is organ S value that is defined from the MERT committee. So by simply multiplying the accumulated activity with the S value, a MERT committee had suggested we can new methodology that we can calculate the absorbed dose at each target regions. So for your reminder, this absorbed dose gray had a unit of joule per kilogram, and the accumulated activity, which I introduced in this slide, had the unit of becquerel second, and this is defined as the total number of disintegration in the target region. And this S value is organ level S value that is defined by the MERT committee, and this one has a unit of gray per becquerel second. And from now on, I will be explaining about this accumulated activity and organ S value in the following slides, and how to calculate the organ doses based on the MERT schema. So continuing from the previous slide, this is the absorbed dose calculation method. And we talked about the accumulated activity, and also what is, I'm going to talk about what is this S value. So this S value concept is defined from the MERT committee, and this is defined as the absorbed dose to a target region per unit activity in a source organ. So for example, when we target on calculating the radiation dose in the lung, so absorbed dose of a lung per unit activity from a source organ. This source organ can be anything. For example, we will consider source organ as a heart. So per unit activity from the heart, and that delivers the energy to the lung. So this is a new concept of S value that is defined from the MERD committee. And this S value depends on the radiation type, energy, and anatomical relationship of organs. And this can be calculated as this following equation. And I will be talking about more details of these parameters of this equation in the following sections. So this S value can be calculated based on this equation, or it can be also simulated using Monte Carlo simulation based on the generalized mathematical phantom that is called average man. So this figure on the right bottom shows the mathematical phantom that is used for calculating the organ level S values. And as you can see, this average man phantom has a very average size organ and distribution throughout the body. Also, when you calculate the S values, it's based on the assumption that all the organs has the uniform activity and also the medium distribution. So they have suggested this assumption to simplify the calculation procedure. However, in the real situation, the radiation distribution inside the organ and also the organ medium distribution is not uniform. So it has heterogeneous distribution. And there already exists a large database of this S values for various radionuclides. For example, there is a MERD pamphlet number 11, and they provide many organ S values depending on your target organ and source organs. And if you're interested, you can check up on this pamphlet number 11. So from now on, I will go through each step of MERD-based organ dose calculation method. And I will be talking about each step of the MERD-based dose calculation procedure. And as I mentioned previously, we firstly need a pharmacokinetic distribution of the radiopharmaceutical to properly calculate the radiation doses. So first of all, we are going to assume a case of dynamic imaging here. So as an example, we need to take a series of PET scan to make a time activity curve. This is a case of a patient case of using a gallium-68 Nota RGD radiopharmaceutical, and they take 8 different time series PET scans, starting from 1 minute until 87 minutes. So we will firstly need this series of PET scan. And I tried to divide the procedure of MERD-based dose calculation into 5 steps. And firstly, we had the dynamic imaging. And as a first step, we need to define the source and target organs inside the patient body. So since in the patient body, radiopharmaceutical are distributed in the whole body area and the organs, and you need to remember all the organs can be either source or target. So for example, if we want to calculate the absorbed dose of the liver, we need to take into account of the radiation sources that is distributed in the liver itself. And also there is a neighboring organ such as heart, lung, intestines, and the radiation pharmaceutical distribution inside these organs can also deliver the energy to the liver. So firstly, we need to define the target organ and also the source organ that will deliver the energy to the liver. Once we define the source and the target organs, as a second step, we need to obtain the time activity curve of the source organs. and then calculate the amount of the activity and the time spent in the source. So at this step, we are going to calculate this A tilde. And for your reminder, this was the equation for the observed dose calculation based on the Merz schema. And in the step 2 and 3, we are going to calculate this A tilde to finally calculate the observed doses. And at this step, we're going to calculate the cumulative activity A tilde or the residence time. And this step will be most troublesome and many errors will occur at this step because there are lots of variation exist, including metabolism, distribution of the radiation sources, and also disease states. So for the step 2 and 3, I mentioned that we are going to calculate the cumulative activity. So this cumulated activity is defined as the amount of activity that is present in the source organ during the length of time for which the activity is present. So we have taken, based on our assumption, we already have the dynamic PET scan, and depending on the target and the source organ, we're going to draw a region of interest, ROI, and on the different PET images at different time points. And then we will have the time-based activity information for each target and also the source organs. So we can draw a time activity curve, as you can see in this figure on the right top. And by integrating this area under curve of the time activity curve, we can calculate the cumulated activity of A tilde. So as I mentioned, cumulated activity is defined as the amount of total activity that is present in the source organ. And it means the total number of radiation disintegration of the radionuclide inside the source organ. Another similar terminology that you can use instead of the cumulated activity is the residence time, which is also called as average lifetime. And this is defined as average lifetime of the radionuclide inside the source organ. So based on the assumption that the time activity curve can be fitted with the exponential function, we can simply calculate the residence time based on this equation by dividing the cumulative activity with the injected dose of the source organ. So, and this will mean the number of disintegration per unit activity. So to summarize, at step 2 and 3, we're going to calculate this E tilde, and here we are going to draw an ROI on each source or target organ on the PET images at each different time points and draw a time activity curve and integrate the area under curve to have the cumulative activity. So moving on to the step 4, at this step, we are going to calculate this delta I parameter in this equation. And here, we calculate the total number of energy that is emitted by the radioactivity inside the source organ. And depending on the radiopharmaceutical or that is used in your study, each of radionuclide have different emission and also energy and frequency. So depending on their characteristic of radionuclide, you will have the different energy delivered to the target organ. So we're going to consider these factors in step 4. So the calculating each characteristic of radionuclide, here we introduce a new parameter that is called equilibrium absorbed dose constant, which is shown as delta I, and unit of Gray kilogram per becquerel second. And this is defined as the energy emitted per unit cumulated activity. As I mentioned, This delta I value depends on the radionuclide and emission type, and this can be calculated as this equation. And here, this EI means the average energy of ith emission, and NI means the relative frequency of this emission. And this number is a conversion factor to change the MeV to the joule. And depending on your radionuclide, if your radionuclide emits X-ray, gamma ray, beta ray, and also other radiation particles, you need to calculate each of the delta I factor depending on the emission type, and then sum it all together, and you will have this absorbed dose constant finally. So in the final step 5, based on this equation, we are going to calculate this phi I, and this is the step of calculating the fraction of energy emitted by the source organs that is absorbed by the target organ is determined here. So for example, when we calculate the dose that is delivered to the liver, the radiation from the stomach to liver will be different from the radiation from the kidney to liver, because their anatomical distribution is very different, and also their so this factor depends on the patient anatomy, and depending on the patient anatomy, the fraction of energy that is emitted by the source and that will be absorbed by the target will be different. So we're going to calculate that factor in this step 5. So at this step, we're going to introduce a new parameter that is called absorbed fraction phi. And as I briefly introduced, this is defined as the fraction of energy that is emitted by the source organ and that is also absorbed by the target organs. So depending on your source and target organs, this absorbed fraction will be different, and it will depend on the amount of energy reaching the target organ, and also the volume and the composition of the target organ, and also the type and energy of the emission. And most importantly, it depends on the anatomical relationship of the source and the target pair. This absorbed fraction has to be determined for each type of emission from a radionuclide for each source and target pair in calculation. So once you define your source and target organs, you need to calculate this absorbed fraction based on the Monte Carlo simulation using this kind of mathematical phantom, and calculate the absorbed fraction depending on the type of emission of the radionuclide and sum all of them. So yeah. So we went through all 5 steps of the calculation of radiation procedure. Throughout this whole step, we have went through the calculation of cumulative activity, calculation of delta I, and also calculation of phi. And this is the mass of organ. So throughout every step of organ dose calculation, we will be able to calculate the total energy absorbed dose at the target organ. And the final equation of the absorbed dose will be like this for your reminder. And we calculated every single parameters here. And then we are going to divide this total absorbed energy with the target organ mass of mk, and this will be equivalent to the A tilde times the S value. So the procedure that we went through might sound very complicated. However, you don't need to worry about this because, as I mentioned previously, there is already a large database of organ S values with different source and target pairs. As you can see in this table. So if you want to calculate the organ doses, you might need to look up on the database or library of the organ-S values and find the proper pair that you are interested in. So this is the end of the procedure. We went through the whole procedure of the organ-based dose calculation procedure. And finally, I would like to show you a simple example of organ-based dosimetry using a commercial program called Olinda EXM. So there are already several commercial software that can calculate the organ doses. And here I would like to introduce you a program called Olinda EXM, which is organ level internal dose assessment with exponential modeling. And this software is developed by the Radar Group, and they contain a database of organ-S values over 1,000 radionuclide, including alpha emitters. And they also supports for the Voxel-based realistic phantoms for adults, children, pregnant women, and also some phantom models for the animals as well. They are able to modify the organ masses to generate some more patient-specific values, and also they have ability to assign the radiation activity to the walls of the hollow organs. There are also other commercial software called MurDose or BigDose, and recently in this field, I think there are more available commercial softwares. But here I would like to introduce Olinda EXM for an example. So if you open this Olinda EXM program, you will see this kind of window. They have 5 different tabs. This is a main input form. The tab you need to provide nuclide input, model input, and also kinetic input. So when you just started this program, you will see nothing here regarding the nuclide and model information. And first of all, to start, so you will need to select the proper radionuclide that you used for your study. So here I chose gallium-68. And then as a next step, you will need to select the proper modal input for that will correspond well to your patient study. Here I have chosen the adult female, but you also have other choices as adult male, 1, 5, 10, 15-year-old child, also newborn baby, and there's also other options of 3 months, 6 months, 9 months, pregnant women. And also there are other options that you can select regarding on your study. There's an option of prostate gland, cavity, spheres, and head and kidney models. So this, the most important part of using this Olinda EXM software is to providing the kinetic information of your patient study. So going back to the page number 17, where we calculated the cumulative activity by making the time activity curve. And from that information, you can also calculate the residence time. And depending on your organs, you need to provide the residence time information here. And at this step, you can also have the voiding bladder model if your patient went to restrooms in between the dynamic PET scans. And you can also fit the data to the models and check the results here. After providing the kinetic input information, when we go back to the main window, you will see that the nuclide and model information is filled. And if you click this doses value, You will have the output data, as you can see in this window, depending on your target organs and also depending on the radionuclide that you used in the study, you will have the effective dose equivalent values for many different organs, as you can see. So using the commercial software will be very simple to calculate the absorbed dose at each different organs, but the most important step is to provide the proper kinetic information from your dynamic PET scan. So I would like to summarize the lecture today. So we talked about the organ-based dosimetry using the MERT schema specifically. And this organ-based dosimetry is calculating the absorbed dose inside the internal organs of the patient body. And this calculation method is suggested from the Society of Nuclear Medicine MERT Committee. And this organ-based approach is used as the gold standard in the nuclear medicine field because the procedure of organ-based dosimetry is rather simple and it is very fast for the calculation since we are already using the already established large database of organ S values. And also, as I mentioned previously, this calculation of absorbed dose in organ-based dosimetry is based on the standard model of human anatomy. So if you use this approach, it is very useful in terms of providing the dose assessment for a general population. However, the major drawback of this organ-based dosimetry is that this is not the patient-specific dosimetric approach. Because since just mentioned, this calculation of organ doses are based on the standard model of human anatomy, where we use the average mathematical phantom that has the fixed anatomical information and distributions. And also here we assume that inside the organs, the sources are distributed uniformly and also media distribution is also uniform, which is also not real in a real patient body. So the major drawback of the organ-based dosimetry is it is not patient-specific, but recently to overcome this kind of problem, there is a new technique called Voxel-based dosimetry approach, and where we calculate each radiation doses on the voxel level, not in the organ level. So, and I guess this voxel level dosimetry will be given lecture by the Professor Jae-sung Lee in the next session. And this is end of my presentation. Thank you for your attention, and any questions or comments?
Do you have any comments or questions or comments for the organ-based dosimetry, or we can discuss on the last session? So I would like to thank Dr. Min-sun Lee. Yeah, and we will have a 10-minute break, and I think we can start at 25. So let's meet at 10 minutes later. And I would like to inform that we are actually, there is a questionnaire. So if you have time, please fill out the questionnaires that we can actually, we welcome you all the comments and questions. Thank you very much, and meet you again at 10 minutes later. I think it's time, so we will, Professor Jae-sung Lee will deliver us a lecture regarding Voxel-based dosimetry. So please welcome Professor Jae-sung Lee.
Thank you. Can you hear me?
Yes.
Okay. Yeah, thank you for introduction again. Yeah, so I'm Jae-sung again. So this is my second lecture. That is, about voxel-based, dosimetry. So as Dr. Lee told you in the previous talk, the organ-based dosimetry is based on the standard model of human anatomy. In addition, that in the organ-based dosimetry, the uniform activity in the organ is assumed. However, actually, the activity is not distributed uniformly in the source organ. So that is why the conventional, the organ-based dosimetry has limitation in each accuracy in those estimation. So on the other hand, the voxel-based dosimetry, so that is mainly based on the voxel-based Monte Carlo simulation, is more accurate than organ-based dosimetry, because in the voxel-based dosimetry, each voxel are regarded as a single organ. So I mean that each voxel, is regarded as a source voxel, and the target voxel. So that is why that the voxel-based dosimetry is independent from the standard human anatomy, and we can also assume the inhomogeneity of activity distribution inside of each organ. So as I told you, the voxel-based dosimetry is mainly based on the spectricity or opacity of each individual. So the more accurate, personalized, dosimetry is possible. We also, we can also consider the heterogeneous activity and medium distribution. But as I told you, that the voxel-based dosimetry is mainly based on the Monte Carlo simulation. So it usually takes so long time. So this is why that some simple but fast approaches has been also proposed. So these simple but fast approaches include dose point corner method and voxel S-value method. But the limitation of these simple but fast approaches is medium heterogeneity is not. I'm so sorry. Actually, I told you that the limitation of this simple method is that the medium heterogeneity is not common. So let me tell you, each of these simplified methods. Actually, the dose point kernel is a radial observed dose distribution. I mean that so let's assume there is a point source here, okay, and actually that then we can measure the dose distribution around this point source, and if usually that we assume the homogeneous water medium, okay. Then once we calculate, we obtain this radial observed dose distribution, dose point kernel. We convert this point kernel with activity distribution. Then we can estimate dose distribution, one-dimensional dose distribution, with the assumption that the point source, our activity, is distributed in a water medium. Okay. Actually, this one-dimensional calculation is quite fast, but because we have assured the homogeneous water medium, it cannot be applied to the heterogeneous medium. How about voxel S value? Actually, that I can say, I would say this voxel S value is in a 3-dimensional, the version of this dosimetry. Actually, in this method, we assume 3D volume, okay? 3D the homogeneous medium, usually water medium. So there is source voxel here and target voxel. So around this source voxel, every voxel can be target, okay? And usually using the multicolor simulation, we can calculate how much energy originated from this source voxel is transferred to each of the target voxel. So this is voxel Y's voxel S value from voxel I to voxel Z. Okay. So yeah, if we multiply the activity, the cumulative activity of I's voxel and this voxel S value, and add all of them, then we can calculate the radiation dose transferred to the voxel Z. Okay. Actually, this the operation is the same as convolution operation. I mean that the convolution of cumulative activity and voxel S value. Okay. Yeah. So yeah, actually, this equation looks quite similar to the model schema that Dr. Lee introduced in the previous talk. So usually we say this is a kind of voxel level in the model schema. Okay. Yeah, but by the way, anyway, this method is performed under performed with the assumption that homogeneous in water medium. So this method is, although this method is also fast, but the heterogeneous medium is not assumed. So usually it is applied to the homogeneous medium. So in this slide you can compare the dose map calculated using direct multicolor simulation and the dose map calculated using the single dose corner with voxel S value for water. Yeah, actually, that this method, the voxel S value method, looks quite accurate for the organs that has water equivalent tissue in terms of density and atomic number or something like that. But in other organs, that is quite different from the water. The error of dose calculation is quite high in comparison to the dose map calculated using the multicolor simulation. Yeah, so let me move back to the multicolor simulation. So yeah, as I told you, the patient-specific, the voxel-based dosimetry, is done mainly using the multicolor simulation. Actually, that the multicolor simulation is quite accurate because that the general radiation processes such as generation, trace, interaction, detection, all of them are followed by this multicolor simulation. Yeah, actually, that the many multicolor simulation, the toolkits are available now, but some limited the number of multicolor simulation toolkit supports the radiation dose calculation. So in my lab, we have used, we mostly have used the gate simulation tool. So that is based in Ziampa the code. Actually, that this slide shows some example of those maps that was calculated using the gate simulation. So actually, that this slide shows those distribution the overlaid on the calculated using this gate simulation, overlaid on the mouse CT data. Okay, and this is another calculation based on gate simulation. I mean that the dose distribution around iodine 125 seed, the implanted for to treat for the therapy of prostate cancer. Okay. So let me briefly tell you, what's the procedures in this voxel-based dosimetry. Yeah, as I told you, for the patient-specific, voxel-based dosimetry, we need, the patient images, especially, the attenuation image and the emission images. Okay. So once they are given to the Monte Carlo simulation tool, the simulation tool provides us the dose map, the result of the dose calculation. So this result of this calculation is generated as 3D image. Yeah, so look at this. So these are this is gallium, the opacity data. You can see here, and image should be a kind of dynamic data. We need multiple time points to obtain the cumulative activity. Okay. So anatomical data like CT image is used as voxelized phantom in the gate, and that the image pixel value of the CT, I mean the CT house field unit data is converted into some tissue type, each attenuator. Okay. Yeah, actually, that the activity data is regarded as voxelized source in the gate simulation. So in this case, we have used the PET data. Okay, but this activity data should be converted into the activity. I mean that usually the PET or spec data is has the unit of count per sec or something like that. So we need some the conversion factor to convert the count rate into the activity. Okay. So we should measure this conversion factor for each of our scanners. So as I told you, once this the attenuation activity data is given to the simulation tool, this simulation tool produce voxelized dose maps. Okay, so 3D dose maps in the gray. And uncertainty map is also created. I mean that the uncertainty in the dose calculation is also given to us. So let me show some typical result of the voxel-based Monte Carlo simulation. So this is opacity data that we given to the simulation tool. Then this gate simulation tool provide us this 3D dose image. Okay, so and actually that it has the unit of gray or something like that. So we can also utilize this simulation tool for small animal studies. So in this study, actually we compare the radiation dose distribution of 3 different radiopharmaceuticals for therapeutic purpose. One of them was the lutetium 177 labeled folate. Actually, that we intended to develop some pharmaceutical therapeutic, the theranostic, radiopharmaceutical, targeting for folate-rich receptor. So we directly labeled the lutetium to the folate. But as you can see here, the kidney uptake was quite high. It led to the high kidney dose, as you can see here. Yeah, actually, that in this energy deposition map, the unit of each voxel is joule per second per voxel. Okay. So this is this is for the second tracer that we have tried. Actually, that we labeled rotation to the ionized oxide nanoparticle because we wanted to see whether the ionized nanoparticle can modify the excretion route of this the radiopharmaceutical. So as you can see, the uptake of this tracer to the kidney was dramatically decreased, and resulting in the reduction of radiation dose to the kidney as well. Okay. However, if we label the rotation 177 and folate to the inox nanoparticle, actually this inox nanoparticle enable the reduction of kidney uptake, and the result and the reduction of radiation dose to the kidney as well. Okay. So if we compare the observed dose to kidney, a critical organ, relative to the rotation labeled in folate, very the 91, compared to this, actually, if we utilize another particle here, we can reduce the radiation dose like that. Okay. So let me now move back to the direct Monte Carlo simulation. So as I told you, the Monte Carlo simulation, direct Monte Carlo simulation, is more accurate approach than any other, because that we regard heterogeneous activity and medium distribution. But the downside of the Monte Carlo simulation, limitation of the Monte Carlo simulation, is its expensive computation cost and time. It takes very long, very long. So it is very hard to use it for routine critical purposes. So this is why that Minson and I have developed some new approaches to fast but accurate voxel-based dosimetry. So one of them is multiple voxel S-value approach for heterogeneous medium with non-uniform activity distributions. And the other method is deep dose, a voxel dose estimation method based on deep convolutional neural network. Yeah, actually, that the multiple voxel S-value approach is a kind of extension of single voxel value approach to the multiple ones. As I told you, that in the conventional single S-value approach, we just assume that the point source is located in the water medium. So I mean that we have just used this dose quantum for the voxel-based dosimetry. Yeah, but the reality is that our body is not simple water. Okay, so in lung we should use larger corner, and in the air the corner get larger, and in bone the corner width should be the narrower than water. Okay, so in this multiple voxel S-value approach, we pre-calculated all of these corners for different tissue types. Then, by applying the convolution between the activity map and each of these dose corners, we could generate this density-specific dose maps. I mean that this dose map is calculated with the assumption that all of our body is air. And this one, we assume that all of our body tissue is lung, water, and blood. So maybe this dosimetry is only correct in lung equivalent tissue, and this dosimetry would be correct only in the water equivalent tissue. So that is why we multiply the binary mask for each specific tissue types. I mean that this guy was multiplied with the binary mask for water. I mean the water equivalent tissue. Then we can obtain the mask dosimetry like that. Okay. If we add all of them, we can acquire final 3D measurement dosimetry like this. Yeah, the accuracy of this multiple voxel S-value method depends on how many medium that we assume. Yeah, actually, that if we regard only single tissue type, I mean that water, so this is equivalent to the single voxel S-value conventional approach. How about 4 different tissues, air, lung, water, blood? It might not be sufficient for our body, because there would be some other tissue types rather than these 4. So how about 6, 8, 10, or 20? Yeah, we can expect that as the number of the voxel S-value, voxel S corner increase, the accuracy of this method will also increase. So compared to the single S-value method, the multiple voxel S-value with larger number of tissue types, different tissue types, yield that more accurate the dosimetry compared to the direct multiple simulation. So this is the error map, absolute difference. So you can see error is quite the ignorable, except for the lung and some tissue types. But mostly these organs are affected by the respiratory motion. Okay. So we have also applied these approaches to the Lutetium 177 data data. Okay. So these corners, multiple corners for air, lung, and water and blood. Okay. So the spectroscopy data was used, and 200 millicurie Lutetium 177 was injected, and we acquired image data, the 4 hour, 24, 48, and 120 hour after the injection. We applied the same method. I mean that we performed the convolution between the time integrated activity, cumulative activity, and air, lung, and water and blood. Then applied it generated those maps, and then we multiply mask images to obtain final those maps. Okay, by adding all of these maps. So this is the result of Monte Carlo simulation, single S-value and multiple S-value. Okay. So the multiple S-value showed smaller error than single S-value. Yeah, so I think that this multiple voxel S-value method would be quite feasible, because the calculation time would be much shorter than direct multiple simulation. I mean that the time consumption for direct Monte Carlo simulation, is about 10 days. Even we have used 5% of the data. But if we use all of the count, actually it takes a lot of time. But this S-value based method takes a much shorter time. However, if we use 6 or 8 or higher number of voxel S values, computation time is around 1 hour. How do you think? Is 1 hour acceptable? Maybe not. So that is why that we wanted to develop faster method based on the deep neural network, deep convolutional neural network. Actually, in this method, that we have trained convolutional neural network so that it can generate dose rate map once we give CT and activity data as input. I mean that we trained it with the reference data, the Monte Carlo simulation data as a reference for this training. Okay. So for the network training, so we tested this method using the Gallium 68 RGD PET-CT data. So from the 8 patient data, we extracted about 320,000 patches and used it. And the cost function was the error between the direct Monte Carlo simulation based and convolutional neural based those based. Training time took about 100 hours, but once the network was trained, it generated the dose map very quickly. So the left figure shows the result of Monte Carlo simulation. It took about 10 days with 5% data, and the right one is deep dose computation, deep dose result of the deep dose. That only took about 3.6 minutes. That is much shorter than Monte Carlo simulation. Yeah, so as I told you, that the multiple voxel value approach took about 1 hour, but all the this deep dose method provide us almost the equivalent dose map, but the computation time, is much shorter. The error between the deep dose and Monte Carlo simulation was quite low, and you can see the error in the long region was also decreased, and boundary was also decreased. And the profile also confirms that dose distribution between the direct Monte Carlo simulation and deep dose method is quite negligible. Yeah, so in my second lecture, I told you what is the limitation of organ-based dosimetry and what is the advantages of the voxel-based dosimetry that if we can do. And the voxel-based dosimetry is very patient-specific, but we need PET-CT or SPECT-CT data because we need accurate the activity information for each 3-dimensional voxel. The Monte Carlo simulation is a standard method for this voxel-based dosimetry because it tracks all of the radiation process. But the very slow computation time, long computation time is the main limitation of Monte Carlo simulation. So that is the reason why we have developed voxel S-value approach and deep dose method. So in the multiple voxel S-value method, we should create dose corner for each different type of tissue medium. Then we should apply the convolution between these multiple dose corners within activity data. And then by integrating all of such information, we can generate 3-dimensional dose map. Yeah, each accuracy is quite good, but it's still slow. It takes about 1 hour. But the deep dose map that is based on the convolutional neural network is a very fast method to infer dose distribution map from the density and activity information. Okay, that's it. So do you have any question? Yeah, if you have any question, you can ask me directly or you can leave the message. Yeah, either way is good for me. Yeah, if not, let me ask Dr. Saw to take over.
Okay, yes, I think, so I think there's one question from Dr. Asmar.
If we want to do dosimetry for either 130, how long and how many readings we should take? I'm not sure. Dr. So do you have any answer for this question?
Okay, yeah, actually, like theoretically, some articles refer that to the time points that are needed for the dosimetry, says that it needs like at least 3 to 4 times of the half-life, which may be the effective half-life. So you might need the if you know the effective half-life of the iodine-131, you may have like at least 3 times of that. But it may be too long for like iodine-131. So, but at least it is saying that you need to check the peak and the declining of this radiopharmaceutical in the source organs. So if you check the declining, and at least at that declining point, like at least 2 or 3 time points may be feasible to get a quite more accurate result of the dosimetry. So yeah, so that will be the answer. But like but too many imaging time point is actually very hard, both for the patient and the clinicians. So there is an also attempt to reduce much as possible. Okay, I think that would have answered. Okay, so I think now is the question and some discussion session. So if anybody have some questions regarding not relevant to the lecture, but regarding the dosimetry, I think we can freely discuss at this moment. Or if like someone could exchange some experience of dosimetry study, it will be also nice for us to hear, because we also don't have that much experience of dosimetry right now regarding especially the PRRT. We have just started the therapy, so we are also the beginners. So if someone could share us, it might be good. Okay, I think there might be no extra questions or comments. And actually, we have put a link for the questionnaire. So I think if you want to give us some further comments, I think you can put it, you can write down on the link that then we can actually more update our contents for the future workshop. Although it's quite early, I think we can finish the session. And before finishing it, I would like to invite Professor Jae-sung Lee for closing remarks.
Yeah, thank you again for your attending and your attention to the our presentation. Actually, because that when we visited Bangladesh, actually I had a chance to give you the lectures on the dosimetry. So some of the presentations were the overlap with what I gave you before. So that is why you may not have many questions this time. But if you have any questions or something like that after this meeting, you can ask us using the email. Okay, thank you very much. See you next time.
Thank you.